Morning, everyone. At least it's morning for me. So I'm Dr. Romulo Bainy, and I'm going to be presenting to you some screening studies that we did for susceptibility of subsynchronous control interactions using EMTP. So just going back to the co-authors, we also have Jared Mraz, Dr. Normann Fischer, and Dr. Brian Johnson. And it's a pleasure to be here presenting to you about this subject. Okay, so the presentation is organized in 4 main parts. First, I'm going to introduce you about some concepts about subsynchronous oscillations, or SSO. Then I'm going to talk about using EMTP as a tool for us to study these events. And then I want to share some of the studies that we performed using EMTP. And then finally, jump for some conclusions that we got after our studies. Okay, so let's start with subsynchronous oscillations here. So here, just like an introduction about this topic here, I brought this table here, and we have basically 3 main types of devices. We have the series capacitors, we have our power electronic devices like HVDCs, like a type 3 or type 4 wind turbine. And then here we have like a torsional mass, for example, like a wind shaft, for example. And here we can have, like in this table, the interactions that may happen when we have these devices connected in the same grid. So, for example, if we have series capacitors and these power electronic devices, in this case, we are focusing in the type 3 wind turbine, we may face some subsynchronous control interactions. Another example here is in case we have series capacitors and torsional masses in the system, we may face some subsynchronous resonance. And in case you have the same torsional mass and the power electronic devices, then you may face subsynchronous torsional interaction. But here today, we are focusing in subsynchronous control interactions. And then we can divide the SSCI in 2 main parts. The ones that we call series capacitors, oscillations, or SSO, and the ones that are weak grids, SSO. And what basically, like the basically difference that is that the series capacitor is going to be caused when we have a radio connection between our type 3 wind part and a transmission line that has series compensation, for example. And the weak grid SSO is going to be caused by a type 3 wind park that is connected to a weak grid, which is basically when we have like a high impedance or like a low, which is also a low short circuit radio. So just like an overview, so we can just summarize a few things. So it's important to highlight that SSCI, it's not a mechanical interaction. It is in fact it's a pure electrical interaction of the system. And this interaction is going to be between the control of the turbine with our electrical network. And cases that were found in real systems, they show that wind turbines that are the type 3 ones that are readily connected to a series capacitors from a line that is compensated, and they are more susceptible to face these type of problems. So I want to jump here and into some real world SSCI events. They've been happening in several parts of the world. I just brought a few here that we can focus today. And here we have a case that happened in Texas in 2009. Here, what happened is that this line between Lone Hill and Agile, it faced a fault. That fault disconnected this line. Because this line was not connected anymore, we had this wind park here readily connected through this line, which has series compensation. And here, 150 milliseconds after this line was removed from the system and the fault isolated, it was identified some subsynchronous oscillations in the range of 20 to 30 hertz. And the way that that this was fixed for this system is that the series compensation of this line was reduced. Another case that happened also in a real world system was also in Texas, but this one in 2017. And as you can see here, we have like this representation of the system, and we had three events that caused, one event that caused this line to open, and another two events that caused this line to open. And whenever like one of these lines, either these or these, is open, we are going to have some of these type 3 wind parks readily connected through this long line here that has series compensation. And basically that is the interaction that, that's the situation that caused the SSCI to occur. In this event, we also, they also measure oscillations between 20 to 30 hertz. And the reports that there was no damage to the wind parks in this situation. Also, those type 3 wind turbines, they had mitigation measurements that the manufacturer of the turbine installed there and programmed there, but they were not enough to prevent the SSCI to occur. And the main conclusion here is that you have to do careful study about like all the possible topologies of your system, like lines that are disconnected and situations when you may have your wind parks readily connected to the system, readily connected to the system with the series capacitors. And so basically the conclusion is that you need to do a careful study to identify those situations. Okay, so this was just like a background, a few events. If someone is more curious about that, I can share a reference that has more of those events and that has like more curves and more information as well. So now I wanna talk about how can we use EMTP as a tool to get more information and see the susceptibility of our system to SSCI. So the way that you can do that in EMTP is through a combination of frequency scans. And you basically have in one side, here we have our point of interconnection of your wind park. We have your grid in one side. You have, here I put as a DFIG type 3 wind park. And the way that you do that in EMTP is that you are going to calculate you're going to perform a frequency scan in the grid side, removing all the nonlinear elements, all the wind parks, everything. And then you are going to do the same thing, but this time you are going to do a time domain frequency scan by including by basically adding the harmonic frequencies that you want to study. And with that, you can calculate both the impedance of this side here, the wind park side, and the impedance of the grid side, and then combine them by summing. So you can have the X total and the R total of your system. So the way that you do that is a 4-step process. Like I said, we're going to first perform the grid side scan to get the R grid and X grid. You're going to do the converter side scan, where you're going to have the R and X for your wind park. Then you are going to combine this result, and you can do that in several ways. You can do that using third-party software. You can do that using Excel. You can do that using EMTP, and then finally you can perform a time domain verification, so you can actually get those oscillations to occur. And the system that we use it to do this analysis is a series compensated transmission line here in the bottom. This is a 500 kV, 400 kilometers transmission line that has shunt reactors in both sides. The shunt compensation is set to 60%, and the series capacitor banks are set to 70%. And this line is from a real system. Here we have the wind park that is connected here to this bus here, that interconnects as well to this other line, which has no series compensation. So this is like, overall, this is a hypothetical system, even though the transmission line is a real model. This whole topology is just hypothetical here for our studies. Our wind park was set as a type 3 wind park, where we are going to have 400 towers, each one with 1.66 MVA, and that's going to result in 666.8 MVA of total power. We set this to Q, control mode, the control mode of the reactive power, and to 9.4 meters per second, the wind speed. And I'm just going to run through all the steps that you do. So step 1 to 4 being the grid side scan, step 2 being the wind park scan, step 3 combining both, and then step 4 a study of the system in time, so we can see the oscillations. So starting with step 1, our grid side frequency scan. So this is a linear scan, simple to do. Basically going to isolate this portion of the system that is our portion that we are interested, which would be like the situation where we have the wind park readily connected in case this line opens. And the curves that we got here for our impedance, we have blue here, the R grid, and the red one is X grid. We have this resonance point here, and we have a few other resonance points as well. When we move on to step number 2, we can see that we are going to isolate the wind park, and then we are going to use the one block that is available in EMTP that is called a TD frequency scan, time domain frequency scan. And you can find all the details about using that block in the manual available with the software. And here is the results that we got here. So we have, for the red here is our reactance, and the blue is our resistance. If we go to step number 3, where we are combining the grid, our series compensated transmission line, with the wind park, which is a situation that is more likely for us to have is more susceptible for us to have the SSCI. We're going to combine these two. And then here we have the combined curves for the reactance in red and for the resistance in blue. Here I have like a few circles here identifying our resonance frequencies. And these resonance frequencies are basically when we have the reactance crossing from the negative side to the positive side. So basically it's when the reactance is 0, that's our resonance frequency, and we have 3 here. In this case, we also know that whenever you have the crossing from the negative this area here to the positive, this means that we have a series resonance. When the crossing happens from the positive to the negative, then we have a shunt resonance. So the numbers here, I also want to highlight them. This is the value of our resistance in these resonance frequencies. So for the first one and the second one, we have positive values. That's basically going to be the damping of our system in those frequencies. And here we can see that between 25 to 30 hertz, we got this negative damping. So basically, this range of frequencies, we can have oscillations that are going to be undamped. And those oscillations, they can occur even if you switch shunt reactor, if you change something in the system. In any of those events, some oscillations may occur, and if they are around that frequency, they are going to be undamped, and then you are going to have some subsynchronous oscillations. And then we can move, so then we can actually see that here. The technology is amazing. So step number 4, we have our transient analysis. And here I want to explain the step by step what I did. So we have a fault in this line here between the end of the line and the breaker. This fault occurred at 2 seconds. And then 100 milliseconds later, this breaker is going to open. And we also have like another breaker here, but I just represented like what we are, like our focus points here. So this breaker is going to open, and then we are going to basically isolate the fault. When we isolate the fault, we have like this brief window here of 100 milliseconds where our fault is still connected to the rest of the system. And then finally here, the fault is isolated. And when we isolate the fault, we have the wind park radially connected to the transmission line that has a series compensation. And as you can see here, we have some critical oscillations here. But it's hard for us to actually, I mean, we can see that it's obviously a low frequency oscillation, but it's hard for us to just calculate this frequency using this signal. So you can do the FFT of your signal, like I did here. And you can see that we have higher components between 20 and 30 hertz. This is the FFT of the phase A. So yeah, this is the step by step. Step number 4. So what we did here was basically like we identified the resonance frequencies. We saw that we have the negative damping. There is which means that this system is more susceptible to have subsynchronous oscillations. And then we finally perform the transient analysis to get the results and see that we actually have low frequency components occurring when we have this wind park series connected to our transmission line. Now I want to share some studies that we did using EMTP. That was just like an example for us, but we are going to keep using that same study. Just here I removed the other side because we are going to talk just in the frequency domain here. And I did 5 studies here for us to see today. The study number 1, I varied the series compensation level of the transmission line. Study number 2 was also a study of variation of the series compensation level, but this time I removed the shunt reactors banks. Study number 3 is a variation of the shunt reactor banks, of the shunt compensation level. Study number 4, I focused in varying the wind speed of the wind turbine and see how that affects our frequency response. And finally, the control mode of our type 3 wind park. So this is a total of 23 cases here. And one interesting feature that you have in EMTP is that you can program your scripts and then have the simulations to be performed automatically as well. So let's start with study number 1, where we are varying the compensation level of our transmission line. So this is done by varying from 50 to 80%, just highlighting that this line was designed to operate with a 70% rate of series compensation level. And yeah, and then the steps here, they are 5%. So when we plot the R total and the X total for these 7 cases that I just showed you, we get these lines here. So you can see that that the higher the compensation is, so we are going to see like the blue line is going to be 50%, and this dark red line is going to be 80%. So the first thing that we can notice there is that the curve is moved to the right. The blue one is here, the dark red one is here. The circles here, they just show us our resonance frequencies, and you can see that they move around according to the compensation level. So I want to focus in this area here, where we are going to have the negative damping or the negative resistance. And here is when we zoom in that area. So here, this first value is for our blue curve, and they are just going to follow this sequence here until the 80% of compensation level. So what we can see here is that we are just looking here at the R total. The bottom graph is for the reactance. So let's focus on the first one, and then I'm going to talk a little bit about the reactance. What we have here is that when you increase your compensation level from 50% to 80%, you are going to have your damping almost 3 times larger. So we start with -10, and then we go to almost -30 ohms, which is more critical, because here we basically have because this is a negative gain, this is a negative damping. This is going to mean that we're going to have like even a higher gain for higher compensation levels. When we check this reactance, the X total here, the total reactance of our system, we can see that these values here, just under the circles, they are the frequency, they are the resonance frequency, where we go from negative side to positive side here. You can also go from positive to negative, but this we are talking about from negative to positive, which is a series resonance. So the frequency also changes. So for 50% here, we have 24.5 for our resonance frequency, 0.7 for our resonance frequency. But when we go to 80% of compensation, then we have 31.1 hertz. So this is basically 7 hertz in a 30% window of variation here. When so now study number 2 is really similar to study number 1, because we are also going to vary the compensation levels, but we are removing the shunt reactor banks. And we have cases 1 to 4 here. And we're also going to go from 50 to 80 hertz. I just removed the 5% step to 10%, just so the graph can be a bit cleaner. And the results that we got for this variation when we remove the shunt reactors bank, they are shown in these 2 graphs here. So again, top part, we have the R total. And then the bottom part, we have the X total. So you can see that the curve is different from the last one. We lose that shunt resonance point, and we lose that shunt resonance point. And the 4 circles here, these the curves are like really close together for the resistance, and they are a little bit farther apart for the reactance. We have the 4 circles here, which are our 4 resonance frequencies where we have the crossover of the reactance. So if we, again, zoom in so we can see what is actually happening there, we can see that the crossover is going to occur in different frequencies, like it happened when we had the shunt reactor banks connected. For 50%, we're going to have minus 80.8, and for 80%, we're going to have minus 26.53. So it's almost the same ratio. So a 30% here of increase is going to be almost 3 times larger, a little bit more than 3 times larger in this situation. And the resonance frequency here also is going to vary from 23.9 hertz for the 50% of compensation to 30.1 hertz. And the reason that I did this study number 2 is just to see how much the shunt reactor banks are going to influence for our studies here, and like the inclusion of them. And then what we need to do next is put study number 1 and study number 2 side by side. And you can see that the results, they are really close. Here I'm just plotting the R total for the study number 1, which is the one with the shunt reactor banks. And then the study number 2, again, the R total, but this time without the shunt reactor banks. And you can see that the values, they are really close together. So for 50% here, we have minus 10.11 when we include the shunt reactor banks. And our R total, when we don't include, is going to be minus 8.8. So the deviation here is going to be around like 2-3 ohms. So in some situations, you can even remove your shunt reactor banks to perform some of these studies. But the results, they seem to be quite close from study number 1 with shunt reactor banks and study number 2 without shunt reactor banks. So let's move to the study number 3. In study number 3, we are going to vary our compensation level of our shunt reactors. This, just to simplify, I'm just going to show 3 studies here. We vary the compensation from 50 to 70%. I want to remember that this line was designed to operate with a 60% of compensation level. And the results that we got are these 3 curves here. So the blue one is going to be for 50% compensation. The red one is going to be for 60%, and the yellow one for 70%. So again, when we change the shunt compensation level, when we increase it, this resonance point and the other ones too, they slightly move to the right. This is a shunt resonance. This is affected by our shunt reactors. These are series resonance. This is also series resonance. Just a reminder, series resonance is when you go from the negative side to the positive side. And you can see that the circles, they are really close together. But we can, with technology, we can do whatever we want. So we can just zoom here and see that, in fact, they are really close together. So a variation of 20% here was an increase of 1.2 ohms, which is less than 5% of our resistance. And the reason, like if we check the X total here, we can also see that the variation was of less than a hertz. So the conclusion of this study is that the variation of our shunt reactor banks just produces a slight change of our frequency. So you don't, it's not like a factor that is going to play a major role in these type of studies. Okay, let's move on to our study number 4 about the wind speed. So all other studies that I showed you before, we were studying variation. So it's basically a parametric analysis of our grid. So we vary the shunt reactor banks, the series compensation banks, series capacitor banks. We varied the shunt reactor banks, and then we also removed the shunt reactor banks just to see how that would affect our study. But now we are focusing in our wind park. And in this study, we have 5 different cases. We are going to start with case number 1, which is 5 meters per second of our wind speed, and we are going to increase our wind speed to 12.5. This is going to result in a variation of our active power. So we are going to go from 0.07 per unit until we get like halfway through 0.51 or 9.4 meters per second. And we are going to reach 1 per unit when we have 12.5 meters per second. So let's check the frequency response. So top, again, we have our total, our resistance. The bottom, we have our reactance. And again, the bubbles here, the circles here, they are our resonance frequency, where we have the crossover of the reactance from either the negative or the positive to either the negative or positive side of the graph. The blue, you can see that all the lines here, we can basically see just the green line because which is for the 12.5 meters per second, because all these main responses really close together. We are going to have more deviations, but we need to zoom in again to see these points here, which are the ones again that we are going to have the negative damping. And they are again between 25 and 30 hertz, like we would expect. So let's zoom in there and see. Starting with the R total, if we see here, we have the blue line is for 5 meters per second, and we have the green line, which is 12 meters per second. They are going to follow that order, red and yellow. So basically, the curves, you can just see that the resistance, that the damping is going to increase. It's going to get less negative here, the faster our wind speed here. And that's expected because we know that slower wind speeds are going to result in slower mechanical speeds of our rotational masses there, and that's going to be and that's going to cause us to have a more negative resistance in our rotor if we think about the equivalent system of a type 3 wind park. So basically, the situation becomes more critical the slower the speed is, and usually that's one of the reasons that systems that have wind parks with slow speed still operate, like just generated like a low amount of power. When we have these wind parks connected, your system is more susceptible to face some subsynchronous oscillations. If we check X total here to see our crossover, you can see that the crossover point is going to move again to the right. We start here with the blue line with 26.3 hertz until the green line, which is 30.7 hertz. And this again is a series resonance because we are going from the negative side to the positive side. And the most critical part here for us to see is again that our negative damping is going to get larger when the wind speeds are slower. So that's the takeout of that study. If we move to the study number 5, which is the control mode. Here I kept the speed the same for all cases. So we go from case 1 to 4. The wind speed is going to be 9.4 meters per second for all of them. And the control modes here, they were, the first one is the reactive mode, the reactive power control that we set to 0 per unit. The voltage, the control mode of the voltage, where we want to set the voltage to 1 per unit. The power factor set to 1. And we also represent the QV curve that for that we use the curve available in EMTP. So all these 4 models, they are already implement these 4 control modes. They are already implement in our wind park model available in EMTP, and you can just change them and also set the adjustments that you want. And you also have a few other customizations you can do as well for those control modes. So the results that we got here for the resistance and for the reactance are basically the same for all control modes. So all the curves here, they're going to have basically the same value. The resonance frequency varied less than 1%, so it's basically going to be the same value here and here. So our conclusion was that the control modes, they don't affect much in these types of studies. Again, here we have the resonance frequency around 29.1 hertz, and our damping is going to be a negative damping again of minus 22.37. So other studies that we are still performing, it's just something to bring up, like we are working with the GA18 working group of EEE with the PSRC. And we are studying these SSCI events and looking for like these different systems, connections, situations that we have. And in this working group of EEE, we are still performing more studies. So I just showed you like some preliminary studies that we had and our experience using EMTP as a tool for that. And some other studies that we want to perform here. First one is a tap transmission line. So in some situations, and this is like we had this idea because of like real world situations that we had SSCI occurring, where a transmission line that was already installed that had series compensation was tapped. So it basically includes this bus here, and we have a proportion of the line to one side and a proportion to the line to the other side. But usually they don't change the shunt reactor banks. The series compensation banks, they are the same. And depending on this proportion that because the wind park, the renewable source and renewable sources, they depend of location. So you can't just like move them around. They are there, and then you need to find a way to connect to the system. And usually you're going to tap the line in the closest path of your renewable energy source. So the proportion can be different, and this difference in proportion is going to cause the system to be more susceptible to SSCI as well. I'm going to be present that in future work. So if anyone wants to follow that, can have my email in the end of the presentation and can email me, and I'm going to keep you updated about that. About study, about the other study is this double line that this is based on a system from South Africa. This is a double circuit transmission line, and we have different compensation levels for the line. And also we have a line between these two buses where we can hypothetically connect wind parks. So you can see that this situation here, because we have a double circuit line and different compensation levels, we are going to have a different frequency response of the grid, more resonance frequencies, and depending in which of these lines, maybe one of these lines is disconnected because of a fault or because of maintenance. So all those situations you need to study to see if your system is susceptible to SSCI or not. And we are going to study this system as well. I want to share some conclusions that we got with these studies that we performed using EMTP. First, higher series compensation levels, they are going to result in less damping, more negative damping. We got similar results when we include or we remove the shunt reactor bank, so they don't play a major role in for the SSCI in these studies that we showed. The shunt compensation levels, their influence over the frequency scan is almost negligible there. For lower wind speeds, we also notice that we get less damping, which is expected, of course. The negative gain is going to be higher, and the control mode did not influence the frequency scan. Also, another conclusion that I did include here is that the results that we got in EMTP, they are in accordance with what we find in the literature. So yeah, it was like basically we were able to use EMTP as a tool to perform those studies. So I want to say thank you for the attention, for being here. Again, here, this is my email. You can contact me there in case you want to keep updated about the other studies that we are going to be performing. Just like highlighting here my other co-authors, we have Jared Mraz from Power Engineers, Dr. Normann Fischer with Schweitzer Engineering, and Dr. Brian Johnson from the University of Idaho, and I'm also with the University of Idaho. So thank you so much. And now I'm open for questions.
Thanks, Romulo. We indeed have a few questions, so let's dig in. So let's start with this one. How much of the grid model is included in this type of analysis? And do you have any recommendations when it comes to getting a good grid model for the grid side scan?
So yeah, so these are basically two questions. The first one, so how much of the grid was included in the analysis? In this case, we were focusing in the series compensation, the series compensated line. So we included all the details. In these studies, we didn't include the protection schemes of the capacitor banks, for example, but we included like the whole model of the line, shunt reactors, and the series compensation, the series capacitors. And then the rest of the grid, we just had the equivalent, so we just include the impedance and then an ideal source. And that was enough for us because we were focusing in that series compensated line. If you had other lines in your system, then just like going to the next question, then you would want to have those lines, since those capacitors, they are going to affect your resonance points, and you want to have them for your grid side.
Thank you, Romulo. About the placement of the time domain impedance scanner, can you clarify where exactly would you connect the TD frequency scan tool?
Mm-hmm. Okay, so yeah, I saw that this is for this slide here, slide number 11.
Yes,
yeah. And so here, of course, you can find more details on the manual of the TD frequency scan block. But what you do here is that you are going to calculate the equivalent impedance in 60 hertz for this part of the grid. And then you are going to put that with your ideal source. And after that, you are going to have this bus. This is the point of interconnection. So you are going to connect the block between the point of interconnection and the ground. But you just want to measure the current flowing in the wind park. Like I said, you can find more details, but you are going to connect between this bus and the ground.
And what is the current that you are injecting? What is the current magnitude that you're injecting in the wind park?
So the current magnitude is going to depend, of course, and it's going to depend, of course, in the point of operation of your wind park. But we had like a few variations since I was varying the grid, and that was varying our equivalent of the grid, the part connected here. But the values, they varied between 1.1 kiloamps to 1.3 kiloamps, and I was always aiming to have that current close to 1 per unit of the wind park. So you have to change that slightly because your grid is going to change. For my studies, of course, because I was changing the capacitors and change like the shunt reactors, that changes your equivalent of the grid. So you need to kind of like find that, kind of like tune that current that you are injecting. But for these studies, it was usually 1.1. In some cases, when I was varying the speed, I had to go a little bit. I had to inject a little bit more, and that was around 1.3.
Basically, part of the current is going to the grid.
Yeah, of course. So the current is going to divide. If we imagine here, part of this current that we are in, because the block is going to be here, this is going to be just an equivalent. Part of the current is going to be going to the wind park and the other part to the system. So you want to measure this current and just see if you are getting like close to 1 per unit of your wind park.
All right. What about performing similar studies in the preliminary stages where the wind park manufacturer and the exact design of the wind park are not known yet? Do you have any recommendations for modeling type 3 wind parks in those cases?
Okay, so one of the reasons that we used EMTP for these studies is because the wind park model that is available there, it was adjusted with a collaboration with manufacturers. So it's going to produce results that are close to the real life results. When you build those models by yourself or like try to get that information can be really hard or almost impossible for you to get. So I think that, and of course you don't have access to changing everything in those models, but the thing here is that you can get results that are going to be close to real life results, since for these models they were adjusted with the help with the manufacturers. But like for different manufacturers, of course, you are going to be careful about just assuming that the results are going to be the same. But I think that EMTP has that advantage for you, at least for you to do these screening studies just to see if your system is more susceptible or not to SSCI.
Also, since this study was being done for an IEEE working group in the Prospective Relaying Committee, that's in some ways, that's one of the questions that would be answered eventually when this working group is done. Right now, the working group is in its early stages.
Right. Thank you. Okay, let's keep moving. We still have a couple of questions to answer. Now, what about the wind turbine mechanical system? Was it modeled as a single mass or multi-mass system?
Okay, so again, this is a double mass representation, and that's the standard representation that you have in the wind park block of EMTP.
Right. Related to the protection devices associated with this configuration, did you consider, or do you plan in future to consider actions of bypass of series compensation or generation cutoff protection?
Yeah, for these early studies, I didn't include any protection of the capacitors. So the capacitors, we are not either bypassing or having like any other scheme there, but we are working in having like a more realistic representation of the series capacitors, and then have like a frequency study as well in that side, considering the nonlinear parts of the series capacitor banks. About the protection of the wind park, we were monitoring all the protections that we have there, and just so we don't get into any non-linearity when the protection triggers. So we were making sure that we were monitoring them for all these studies.
And finally, how was the how are these 20-30 hertz oscillations? How have they been measured? At one slide, if I remember correctly, you did show some, or you didn't have any measurements of real. Yes, you did have some real life measurements at the beginning. So how were these measured? What kind of equipment was used?
So for you mean like for the real world events?
Yes.
Yeah. So those those oscillations, they were measured in the current at the ends of the wind park using regular CTs. And okay. Yeah, in this case, we just met, like for the simulation, we just had like the probes there available in the EMTP, and then we for the oscillations, I just did the FFT to measure them.
Sounds good.
Yeah, and so they were just from probably the protective relays that were doing the measurements. So you would have the fact that the cosine and sine filters would have a gain of less than 1 at 30 hertz, and the anti-aliasing filter probably had a gain of more than 1. So you don't really know what the actual gain and how accurate some of the gains were in those magnitudes.
Mm-hmm. Thank you. Well, Romulo, Professor Johnson, thank you very much for being part of this user conference. It was a really insightful and I would say very relevant presentation.